In this video, we're going to begin discussing VSEPR theory. However, the first step of that is actually a slightly older theory called Lewis structures. So we'll begin with that. Lewis structures were a handy way to draw organic molecules. Covalent bonds don't stack together in a big pile like ionic or metallic. They are very specific in their direction. They're very specific in which atoms are connected to which other atoms. So we need a way to identify and show that. A Lewis structure is something like this. This is CH4. CH4 is methane. It is natural gas. If you have a gas stove or anything like that, this is what you're actually burning when you burn. What this shows us is that there is a carbon, and that carbon is bonded. That's what the line between the two elemental symbols shows us. That carbon is bonded to hydrogens. Each hydrogen has its own bond to carbon. So that carbon is showing 4 bonds, one each, to a hydrogen, so that there are 4 hydrogens on it. This is how it actually physically bonds. Methane gas is 1 carbon atom and it has 4 hydrogens attached. If you were to mix them together, if you had 2 separate CH4s, and you left them in a container together for a while, and you could mark them. Let's say we could color code some of these hydrogens. If you come back an hour later, those 4 hydrogens are still on the same carbon. They have not left, they have not reorganized, they are still attached to it. You can heat it up into a gas, you can cool it down into a liquid, you can freeze it into an ice, bring it back to a gas. Those are still attached to it. This is not true for ionics. If you had a sodium chloride, you had pluses and pluses and minus. If you were to dissolve this, and let's say we had marked 2 of them near each other. If you dissolve this in water and then boil the water off to get back your salt, and you come back, these are no longer near each other. Some sodium will be, but say that chloride's still there, the blue sodium may have moved elsewhere. Ionic compounds do not care which counter ion they are near. They only care that there is an opposite charge near them. A covalent molecule very much cares that it stays with the particular atom it is bonded to. And so we need to be able to indicate that quite readily. What you are bonded to changes everything about the molecule. To start with, well, we need to figure out how to make those drawings. Like, how many bonds do different atoms make? For this, we need the periodic table. On the periodic table, we can see various rows. Hydrogen is way over here on the left, helium's over here on the right, boron, carbon, nitrogen, oxygen. In our section on s, p, and d orbitals, we talked about identifying how many electrons were in orbitals. In this section, we're going to introduce an extra component to that. We're going to introduce the idea of valence orbitals, or valence electrons. If we thought about carbon, carbon has 6 electrons. Its protons are 6, its electrons are 6. If we filled it in, 1s, then 2s, then 2p. 1, 2, 3, 4, 5, 6. Carbon at this point is not done filling its S and P. It needs more electrons, and that's actually what covalent bonds helps it do. We'll see a little bit more of this. But if you have a hydrogen nearby with an electron in its 1s, that electron can overlap an orbital from the carbon. When that happens, they pull up adjacent to each other, and you effectively get an overlap system where you have 1 electron from each atom overlapping the orbital of the other atom. As far as each atom then becomes concerned, it has 2 electrons in that orbital. So hydrogen thinks it sees 2 electrons in its orbital. Carbon thinks it sees 2 electrons in its orbital. That makes you more stable. Remember, if your valence shell, if your highest numbered shell, in our case here that's the 2s for carbon, if you can fill that, you're remarkably stable. Carbon needs 4 more electrons before it will fill its 2p. Every time it shares with an atom, it gains 1 electron, which is why it needs 4 atoms. This is why methane is CH4. Valence electrons, however, in terms of our Lewis structures, they are just your highest shell. We don't care about the 1s, it's not getting used for anything. We care about the 2s and 2p because that is the highest shell for carbon. That is the valence shell. How many electrons are normally on carbon in its valence shell? 4. The 2s and 2 of them in the 2p. How we indicate this is you draw a carbon atom, and then around that atom are 4 regions: top, bottom, left, and right. They sort of correlate to the 4 orbitals, the single of the s, the 3 of the p. But in Lewis structures, we don't care where the electrons came from, they're going to get spread out in order to bond. As a result, we just put 1 electron in each of those regions. We spread them out. Well, when I bring hydrogen up, hydrogen also has, well, it only has 1 electron. And so the hydrogen atom just has its 1s with 1 electron in it. So that hydrogen has 1 electron. I can have another hydrogen, it has 1 electron. I can have another hydrogen, it has 1 electron. Move this. I can have 1 more hydrogen, it has 1 electron. Well, I need them to overlap, and so we draw a line between the electrons to show that those are now being shared. The electron on the hydrogen is sharing into the orbital on carbon that needed a second. And we can do this between all of them. If we want to clear this up a little, we can make it look a little nicer. Just draw the neat bond afterwards. And this is where our drawing comes from. We can actually build these drawings by looking at how many electrons we expect to be in the valence shell and then connecting them to add electrons on other atoms. Let's try another example for that, see if we can't clarify it a little. First, how many valence electrons do we expect on the different elements? So hydrogen, well, it's only going to have 1 in its 1s. Boron will have 2 in the 2s and 1 in the 2p. Carbon, we said, had 2 in the 2s and 2 electrons in the 2p. It had 4. In fact, it's based on the column. If you go way over here on the left, the hydrogen is column 1. Beryllium would be column 2. Skip the transition metals and go over here to boron. There's column 3. Carbon is column 4. Nitrogen's column 5. Oxygen's column 6. Fluorine's column 7. The noble gases are column 8. You just count across. How many valence electrons do you have? Just count the columns. If we look at oxygen, it is, well, there's lithium for 1, beryllium for 2, boron for 3, carbon 4, nitrogen 5, oxygen 6. It is the 6th element in its row. Therefore, it has 6 valence electrons. And if we actually draw that just to double check, oxygen is element number 8, so it has 8 protons and it would have 8 electrons. 1s, 2s, 2p, fill in 8, 1, 2, 3, 4, 5, 6, 7, 8. And what we will see is that there are indeed 6 electrons in the 2 shell. Whichever number column it is, that's how many valence you have. It just increases by 1 across the row. So hydrogen gets 1, Boron has 3, carbon has 4, nitrogen has 5, and here's where things get a little tricky. You spread the electrons out to begin with. So if you only have 1, put it in one spot. If you have 3, you spread them out into 3 of the regions. If you have 4, you spread them out into 4 of the regions. And if you have 5, well, remember that each orbital, which is what the top, bottom, left, and right represent, each orbital can only have a max of 2 electrons. They try to spread out first, but once you've put 1 in each, the 5th, in this case, electron, has no choice but to go in an orbital that already has an electron. So that nitrogen, with 5, ends up with what we call a pair. This is a lone pair. A lone pair of electrons means it's on that atom alone. It's not being shared. That nitrogen won't need to share them because that orbital is already filled. The whole reason you want to share it all was to fill those unfilled orbitals. And so nitrogen has 5. Oxygen is going to have 6. So we spread the first 4 out, and then the 5th has to get paired with 1, and then the 6th has to get paired with 1. This leaves us 2 orbitals that haven't been filled yet, and 2 that have a lone pair in them. Keep going down the line. As we get to fluorine, fluorine is in the 7th column, so hydrogen 1, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6. Fluorine is the 7th. Fluorine will get 7 electrons. So spread your first 4 out. Pair a 5th, pair a 6th, pair a 7th. There's only 1 that has yet to be filled. And if you get to neon, to our noble gases, they will have 8. Spread 4 out, pair a 5th, pair a 6th, pair a 7th, pair an 8th. Well, all 4 regions are full. There's only 4 regions around our system, and they all have 2 electrons in them already. This is why the noble gases don't react. And generally that's the case. Somebody did win a Nobel Prize for getting one of them to react. But for the most part, they don't. It's incredibly difficult. Noble gases do not react because they are so stable. Their orbitals are already full. We saw this with filling the S and P in the electron configuration, but it is also part of why they don't show up in covalent molecules. Side note, this makes oil industry a very interesting thing. You've probably heard most of your life that oil is a fossil fuel. It's old life and plant matter and dinosaurs that have turned to oil. But to find oil, we look for helium because it comes up through cracks in the crust, and wherever we find it, that's where the oil fields are. That strongly suggests that if the helium is coming up from the planet and it finds the oil, then most likely the oil came up from the planet. It's actually thought that a large amount of the oil produced in the world is not fossil fuel, it's produced by the planet cycling carbon. Just a fun aside. Back to closing out our Lewis structure video. This is how you identify the valence electrons. For every molecule we want to build, we will then use these to start drawing and combining. So if you have NH3, you would put down a nitrogen, you would put the nitrogen's electrons on, and it doesn't matter where that lone pair is, top, right, bottom, left, is irrelevant. All directions at this point are equal. You can draw it however you want. I just put mine on top right now because that's how I was originally taught. So you put an atom down, you put its electrons around it. You then put down your other atoms, and you pair any unpaired electrons. And so nitrogen here had one unpaired electron on its left. the hydrogen had one unpaired electron, so I've linked them together. And I do this for the other ones. Pair the unpaired, pair the unpaired. If you want to make it look a little nicer then, nitrogen, dash to a hydrogen, dash to a hydrogen, dash to a hydrogen, lone pair on the nitrogen. For ammonia, for NH3, this is how we build the Lewis structure, and then this is the final nice Lewis structure drawing. And we can do this for any other molecule we can come up with. If we wanted to do it for CH2O, so formaldehyde. If you've bought furniture from, well, basically anywhere, your house has a lot of it floating around in the air. By a lot of it compared to safety margins. It slowly leaches out of most of our fake plastic surfaces for wood veneer. So if you have any furniture that, from IKEA and the like, and it has those nice little cheap veneers on top, definitely you have formaldehyde floating around in your room. What is formaldehyde though? Well, it's got a carbon in the middle and the other things are attached. So carbon is our center atom. We put the electrons we expect for carbon's valence. And then we say, all right, well, I'm going to have a hydrogen. So that's going to be there. I'm going to have a hydrogen. That's going to be there. And I'm going to have an oxygen. Well, oxygen has 6. And while I could pair it on the left side near carbon, you don't use lone pairs to do bonding. So it's best to put that 6th electron away from anything else. It just helps visually with drawing. If I had the lone pair near carbon, I'd have to draw from very far away. Well, you pair everything once to get them to attach to each other. But I've got an unpaired electron on carbon. It's not done yet. It hasn't made enough bonds. Neither has oxygen, though. So I could just pair them again. Each of them had an unpaired electron remaining, and so they could connect to one another. Making this look a little nicer, carbon, double bond oxygen. Oxygen has 2 lone pairs. Hydrogen, hydrogen. Now I know as we had drawn it, it would have looked a little bit more like this. In our next video, we will discuss the geometries. The reality is they tend to try to spread out evenly, and so instead of being up, down, left, right, they will shift to kind of spread themselves out. But this is a Lewis structure for formaldehyde. So this is the idea of how to connect various atoms together when they make covalent bonds.